Hello everyone, I am Lu Shoyi from Tongji University. Today I will introduce our paper titled TDFANet, Encoding Sequential 4D Radar Point Clouds using Trajectory-Guided Deformable Feature Aggregation for Place Recognition. Place recognition is essential for autonomous driving, AR, and robotics. 4D millimeter wave radar offers 3D position, velocity, and reflectivity, and remains robust in harsh weather. However, its sparse point clouds and dynamic objects pose major challenges for reliable scene representation and recognition. To address the challenges posed by sparse and dynamic 4D radar point clouds, we propose a novel architecture called TDFANet, which stands for Trajectory-Guided Deformable Feature Aggregation Network. The model consists of 4 key modules: 1.4D point cloud preprocessing, 2. Trajectory-Guided Feature Alignment, 3. Spatio-temporal pyramid deformable aggregation, 4. Global descriptor generation. Dynamic objects like vehicles and pedestrians often appear and disappear, making place recognition unreliable. We address this by using 4D radar's radial velocity to estimate ego motion via ransack and remove dynamic outliers. The cleaned point cloud is then encoded into BEV pseudo-images, and a pillar network extracts spatial features and ego velocity vectors, forming structured spatio-temporal inputs for downstream alignment. Next is trajectory-guided feature alignment. To correct misalignment between sequential BEV features caused by vehicle motion, we estimate displacement using ego velocity and frame rate and convert it to grid-level offsets. These offsets are used for bilinear interpolation, producing temporally aligned BEV features for robust multi-frame aggregation. Now let me introduce the third module: Spatio-temporal pyramid deformable feature aggregation. This module addresses 2 challenges. First, the sparsity and disorder of 4D radar point clouds hinder robust feature extraction. Second, the previous alignment stage only accounts for translation, neglecting rotational motion. To solve these issues, we introduce a 2-stage strategy. First, we construct a spatio-temporal feature pyramid. For each BEV feature map, we apply 3 levels of residual blocks with strided convolutions to create a hierarchical representation. This allows us to capture multi-scale spatial context across time. Next, we present the spatio-temporal pyramid deformable transformer. At each pyramid level, the query feature is refined by combining the current frame with coarser-level context. Deformable attention then aggregates features from aligned frames using adaptive offsets and learnable masks. Finally, a feed-forward network outputs the fused BEV representation. We generate a 256-dimensional global descriptor from the aggregated BEV feature map using an MLP and GM pooling. To train TDFANet, we use the lazy quadruplet loss, which encourages close distances between matched samples and pushes apart hard negatives, improving retrieval robustness. We collected data using a vehicle equipped with 4D radar and a high-precision positioning system. Radar was recorded at 10 Hz and positioning at 100 Hz. The dataset includes 7 sequences across 3 scenarios, with sequences 3:1 and 3:3 captured at different times for long-term recognition. In total, it contains over 25,000 frames split into database, training, validation, and test sets. We evaluated our method against 5 SOTA baselines: Scan Context, MinkLock 3D, PPTNet, Autoplace, and SeqOT. These models struggle with 4D radar due to data sparsity and motion-induced feature shifts. In contrast, our method leverages velocity information and spatio-temporal aggregation, consistently outperforming all baselines across all sequences. We conducted an ablation study, starting from a plain TDFANet with only BE encoding and GM pooling. Dynamic point removal filters out noise and boosts performance. Feature alignment corrects spatial shifts using ego velocity. The spatio-temporal pyramid captures multi-scale context, and deformable attention brings the largest gain by adaptively aggregating features. Each module contributes meaningfully to the final performance. We show retrieval results under challenging conditions, such as dynamic scenes or large appearance changes. Existing SOTA methods often fail in these cases, retrieving incorrect matches. In contrast, our TDFANet handles dynamic interference and captures robust features, retrieving the correct reference frames reliably. Thank you for listening.